Hi everyone, it's B again. In this lesson, we'll keep on learning about exponential functions and how to use them to model different real-world situations. In the previous lesson, we looked at a situation where the balance in an account started at $50 and then doubled every year. This situation was modeled by an exponential function, which we defined as a function that has a constant growth factor, meaning that every time the input increases by 1, the output is multiplied by the same number called the growth factor. We saw the equation for this particular function was j of x equals 50 times 2 to the power of x, where the 50 was the initial balance and the 2 the growth factor. Now, let's consider a general exponential function with input x and output y, an initial value a, and a growth factor b, which means every time x increases by 1, we multiply the output by b. Based on this behavior, how would you express the value of y for any input x? It would be a times b to the power of x. This is the exact format Jake's function followed. We had an initial value, or y-intercept, times the growth factor to the power of x. Therefore, the general form in which we write exponential functions is y equals a times b to the power of x. Let's look at a couple example problems and put this form to use to model some more real-world situations. Here's example 1. In 2015, the population of a city was 625,000. Each year afterward, the population has increased by approximately 4%. Function C models the city's population in thousands x years after 2015. Part A says, assuming a yearly increase of 4%, write the equation for function C. Show your reasoning. Since function C will model the city's population in thousands after x years, the input x will be the years since 2015, and the output c of x will be the population in thousands. Let's start analyzing this function with a table. Since we have an initial population of 625,000, when the input is 0, the output is 625. Pause the video and try to complete the table with the populations at years 1, 2, and 3. To find the population after 1 year, we could find 4% of 625 by multiplying 0.04 by 625, which is equal to 25. Then we would add that 25 to 625 and get 650. This would be the new population at year 1. If you found the values with this approach, great job! Here's the completed table for you to check your work. However, let's look for a simpler way of adding 4% to see if we can find a pattern that will help us write an equation. How can we add 4% to 625 with a single operation? Is it even possible? Here, the initial population of 625 represents our 100%, and if we're adding 4% to it, the population after 1 year would be 104% of 625, which we can find by multiplying 625 by 1.04, which is in fact equal to 650. In year 2, the population from year 1 becomes our new 100%, making the year 2 population equal to 104% of the population at year 1. We would therefore find the population of year 2 by multiplying 625 times 1.04 by 1.04 again, which can also be written as 625 times 1.04 squared. Following this pattern, At year 3, we would get 625 times 1.04 cubed. Notice how adding 4% every year turned out to be the same as getting 104% from the previous year, which translates to multiplying by 1.04 every year. This means we have a constant growth factor of 1.04, which makes this function exponential. Therefore, we can use the form y equals a times b to the power of x. Since we have an initial value of 625 and a growth factor of 1.04, the equation becomes c of x equals 625 times 1.04 to the power of x. Let's look at part B about this same situation. Use your model to predict the year in which the city's population will be 1 million. Pause the video and try to figure out the solution yourself. We can solve this problem using our equation. A population of 1 million is equal to 1,000 thousands, so we can replace c of x with 1,000 and then solve for x. We divide both sides by 625, which results in 1.6 equals 1.04 to the power of x. And then we ask ourselves, what exponent turns 1.04 into 1.6? In the previous lesson, we learned how to express any exponent we need with logarithms. The exponent that turns 1.04 into 1.6 is log base 1.04 of 1.6. Using a graphing calculator such as GeoGebra or Desmos, we find that this logarithm is approximately 11.98, which means the population reaches 1 million almost 12 years after 2015. Therefore, the model predicts the population will reach 1 million by 2027. Let's look at a second example. A water tank with 640 liters starts getting drained, and every minute it loses 25% of its volume. Function W models the amount of water left in the tank after t minutes. Represent the function with a table, a graph, and an equation. Pause the video and try this problem yourself. What is the input and the output of the function? Function W models the amount of water left in the tank after t minutes, so the input of the function must be the time in minutes and the output the liters of water left. Let's start with the table. At t equals 0, we have an initial amount of water of 640. Every minute, the tank loses 25% of its volume. Once again, our initial amount represents 100% of the water in the tank, and if we lose 25% every minute, at minute 1, we will be left with 75% of the original amount. Therefore, losing 25% is equivalent to keeping 75%. How do we calculate 75% of a number? We multiply it by 0.75. Let's use this to fill up the table. After 1 minute, the tank will have 640 times 0.75, or 480 liters of water left. After 2 minutes, we now multiply the 480 by 0.75 and get 360. After 3 minutes, we get 270. We have now shown this function is exponential. Why? Because it has a constant growth factor of 0.75. If you had an error in your work up to this point, pause the video and try out the rest of the problem again. Following the form y equals a times b to the power of x, the equation becomes w of t equals 640 times 0.75 to the power of t, where the 0.75 comes from the fact that every minute we are keeping 75% of the previous volume. Now let's draw the graph. We first label our x-axis with minutes and the y-axis with liters of water left, and then we can plot the points we already have in the table. Connecting the points, we get this curve. But wait! This exponential function looks very different from the previous ones we've made. Can you notice the difference? This graph isn't growing, it's going down. This takes us to the two types of behavior exponential functions can have. The first type is called exponential growth. The situation about Jake's account and about the city's population were examples of exponential growth because the outputs were always increasing. The second case is exponential decay, which is when the outputs are always decreasing, such as in the water tank function. Could we figure out if an exponential function grows or decays just by looking at its equation? Let's examine the equations for Jake's account and for the water tank. What component of these equations determined whether they would grow or decay? For j of x, the outputs were growing because they were being multiplied by 2, which is a number greater than 1. Therefore, for any exponential function in the form y equals a times b to the power of x, if b is greater than 1, the function will grow. In w of t, the outputs were getting smaller because they were being multiplied by 0.75, which is a number less than 1. Therefore, if b is less than 1, the function will decay. However, in exponential functions, we only use positive bases, so b also needs to be more than 0. Let's look at a third and final example. For each given exponential function described, write its equation and explain whether it is exponential growth or decay. Pause the video and read through these two situations carefully. Then try to work them out yourself. Let's look at the first situation. It reads, function p models the ant population in a garden t years since 2010. At the start of 2010, the ant population was 20,000, and it has increased by 13% every year since. To write the equation, let's use our format y equals a times b to the x. The input of this function is t, and the output, p of t. We know the a will represent the initial amount of the population, so it has to be 20,000. We also know that adding 13% every year will be the same as getting 113% of the previous year, which means our growth factor needs to be 1.13. This 1.13 is simply 113% written as a decimal, which is found by dividing 113 by 100. Therefore, the equation is p of t equals 20,000 times 1.13 to the power of t. How does this equation tell us whether this function grows or decays? We know it's an exponential growth function because the value of b is greater than 1. Now let's look at the second situation. Function m models the amount in milligrams of a certain antibiotic remaining in a person's system X hours after taking a 500 milligram dose. Every hour, the amount of the antibiotic in the body is reduced by 44%. Here our input is X, and the output is m of X. The initial amount of the antibiotic is 500 milligrams, so the value of A is 500. Now let's find the growth factor. Just like in the water tank function, let's think about what percent of a quantity is kept after it loses 44%. After losing 44%, we would end up keeping 100% minus 44% of the quantity, which is 56%. Our growth factor should then be 0.56. The equation becomes m of x equals 500 times 0.56 to the power of x. This is an exponential decay function because the value of b is between 0 and 1. In today's lesson, we learned that exponential functions are often written in the form y equals a times b to the power of x, where a is the y-intercept, or initial value, and b is the growth factor. the value of b must always be positive and not equal to 1. We also learned that there are two main types of exponential functions: exponential growth, which happens when b is greater than 1, and exponential decay, which happens when b is between 0 and 1. Next lesson, we'll apply these concepts to some new situations, such as cooling objects and radioactive decay. We'll look at problems where we're given different pieces of information about an exponential function, which will require some additional reasoning to find the growth factors. Once you've finished your guided notes, complete the additional practice in your PDF. After that, make sure to complete the online practice. See you next time!
Hey!